AP Chemistry Screencast 2.7, percent composition as well as empirical and molecular formulas. So there's really two major topics that are covered here, but let's go ahead and cover them rather briefly. As an AP Chemistry student, both of these should be review. Let's begin with percent composition. That's where you have a substance and you want to know what percent of it comes from each element. The larger the molecular weight, probably the larger the percent, right? So take water, for example. What is the percent composition of water? Well, you take some water, you send it off to a lab, and they will come back with these numbers. They'd say for every 18 grams, that's a mole, only 2 of them came from water. So water is always going to be 2/18 by mass hydrogen and 16/18 by mass oxygen, by virtue of the fact that an oxygen atom is so much heavier than a hydrogen atom, that even though you have twice as many hydrogen atoms as oxygen, the mass is still close to 90% oxygen. So let's see, we assume a mole, that makes it easy. 16/18 is 89%. The rest will be hydrogen. As for most of my screencasts, I'm being very glib with significant figures. As a general rule of thumb, you should probably use 3 for AP Chemistry. Of course, the precise answer is use the appropriate number of significant figures. Don't be put off by the fact that I'm being a little inaccurate here. Okay, empirical and molecular formula. It's the simplest molar ratio for elements in a substance. And let's do a sample problem. The actual molar ratio for elements in a substance is the molecular formula. For example, benzene is C6H6, right? It's got, each molecule has 6 carbons and 6 hydrogens. That would be its molecular formula. But if you determine their ratio, you'd simply get C1H1, which is a pretty inaccurate formula for benzene, really, right? There are far more than 1 carbon in benzene. Okay, so let's do a sample problem. We need the empirical and molecular formula for a substance that's 86% carbon, 14% hydrogen, and it has a molar mass of 28 grams per mole. The key for these is not to assume a mole, but since you have 86%, why don't we assume 100 grams so we don't have to do any weird grams. Find out how many moles that is, and that's your mole ratio. So 86 grams of carbon, well, 12 grams is a mole, technically 12.011, meaning that we have 7.1 moles of carbon. By the way, when you do these problems, please do be more precise than this simple example, just in case you have a strange multiplier at the end, and you'll see what I mean. We have 14 grams of hydrogen, if we're assuming 100 grams, but each one is 1 gram per mole, so we have 14 moles of hydrogen. I usually write this as C subscript 7.1 H14, and that's a finished form, it just hasn't been simplified. Now get the lowest common ratio, and that means divide by the little guy, right? 7.1 divided by 7 is 1. 14 divided by 7 is 2. Notice that we do have to do a little bit of rounding, and we get an empirical formula of CH2, but that can't be right if it's 28 grams per mole, because this is 14 grams per mole. Clearly we now have to multiply, we have to double everything, because a ratio of C1H2 is the same as a ratio of C2H4, and we have the added advantage that this represents the actual molar mass of the substance. C2H4, that's ethylene, I probably drew it, there it is. This is polymerized to form polyethylene, etc., and there you go. So this is both percent composition as well as empirical and molecular formulas.